Hello everyone, today I'm here to discuss breast cancer classification, covering the key points of our presentation: introduction, dataset, architecture, experiment, and the conclusion. First of all, I'd like to give you an overview of breast cancer. According to the global cancer data released by the World Health Organization's International Agency for Research on Cancer, or IARC for short. In 2020, the incidence of breast cancer surpassed that of lung cancer in the entire population for the first time, making it the #1 cancer in the world. About 85% of breast cancers occur in women who have no family history of breast cancer. These occur due to genetic mutation that happen as a result of aging process and life in general, rather than inherited mutations. So it is essential to address this issue effectively. Our objective is to develop an algorithm capable of automatically identifying breast cancer in patients using biopsy images. By utilizing advanced technology, we can enhance the accuracy and efficiency of breast cancer diagnosis. To accomplish this, we have selected the BRCACE dataset. This dataset has been built in the collaboration of UFPR laboratory and the PND laboratory. It consists of 2,480 benign tumor samples and 5,429 malignant tumor samples obtained from 82 patients. These samples provide a comprehensive representation of different breast cancer cases for our analysis. Now, let's move on to the model we have chosen, DenseNet, short for Densely Connected Convolution Network. DenseNet is composed of multiple dense blocks. Each dense block maintains the same feature map size, which is ordered through convolution and pooling techniques. The layers situated between two dense blocks are known as transition layers. DenseNet offers several advantages, including 1. Mitigating the issue of gradient disappearance. 2. Enhancing feature transfer throughout the network. 3. Encouraging feature reuse, leading to more efficient parameter utilization. 4. Significantly reducing the number of parameters required compared to other networks. By leveraging these benefits, our model can effectively classify breast cancer cases with improved accuracy and reduced computational complexity.
In each dense block, there's a direct connection between any two layers. The input of each layer of the network is the concatenation of the output of all previous layers, and the feature maps learned by that layer are directly passed to all subsequent layers as inputs. Through dense connection, the gradient disappearance problem is mitigated. DenseNet 201 architecture is composed of 4 dense blocks. The idea is, instead of considering all the layers of the pre-trained network and converting the last convolutional layer consisting of 1920 channels via global average pooling into a one-dimensional feature vector of length 1920, the features were extracted from the lower block 2. The intermediate block 3 and the final dense block 4 of the lower layers of DenseNet 201. After refining the pre-trained DenseNet 201, we use global average pooling 2D on the final output of the last 3 DenseNet module to make the model more robust. This is our model summary. A dropout layer is added to improve regularization and reduce the overfitting problem in the network. The dense layer is used at the end of the network to make it specific to solving the binary classification problem, using the softmax function in the last layer of the network. To address the issue of imbalanced dataset, we used image data generator for data augmentation. We set the room range to 2, which scales the images, and rotation range to 90, allowing the images to be randomly rotated from 0 to 90 degrees. We also set horizontal flip and vertical flip to true, enabling the images to be horizontally and vertically flipped. Our approach includes using a global average pooling layer and a 0.5 dropout to reduce overfitting. We also incorporated batch normalization and a fully connected layer with 2 neurons, using softmax as the activation function for classifying between benign and malignant cases. We set the learning rate to 0.0001, used Adam optimizer, and used binary cross entropy as the loss function. These techniques aim to improve the model's performance and accuracy in classification. These two pictures are the loss of the training set and the validation set, and the accuracy of the training set and the validation set. Precision, recall, and F1 score are important metrics used to evaluate the performance of classification models. Precision means how many of the positive predictions are correct. Recall means how many of the positive cases the classifier correctly predicted. F1 score, combining both precision and recall.
So following the classification report, we also do the confusion matrix. This table is about confusion matrix between benign and malignant tumors. As you can see in the first row is our predict label between benign and malignant tumors. And the first column is our true label between benign and malignant tumors. And our total test images is 1130. Then our true positive means you get predict right in malignant. So that's 636 images. And the true negative is 401 images. And the picture on the right side is what we ran out of the program for this place. And it is the same as the left side. And here's the ROC curve. The ROC analyze provides the AUC under the ROC curve, which tells us how accurate the new scale is, and the larger the AUC under the ROC curve, the more accurate the new scale is. And here's the picture on the right side about ROC curve. And here's our performance. So we have good accuracy to recognize the picture between malignant and benign tumors. And finally, here's our conclusion. The experiment solves a binary classification problems. We built a system that automatically determines whether a patient biopsy result is benign or malignant by systematically detecting biopsy images. And the model validation results. Our accuracy is 98.8%, and our precision is 0.89. Our recall is 0.9. Our F1 score is 0.89, and the ROC AUC is 0.901. And here's our reference. So thank you for listening.